Bloch equations. These are of course phenomenological. It's just ingenuity, intuition of Bloch. Based on the relaxation ideas we have, he wrote down how, whether it's nuclear moment or in NMR or electron moments in ESR, propose these phenomenological equations. So we realize that you go from spins parallel to the applied field, once the RF is on, to anti-parallel, again to parallel, and so on. For part of the thing, it's absorbing energy. For part of the cycle, it's giving off energy. So now, so this comes a bit later. So remember when there was no bath present, right? And then you have this two-level system. Then evolution is that you will get equal populations of the two levels because there's no bath, so there's no question of losing energy, and this Boltzmann distribution doesn't happen. It's only when you have a connection with the bath it happens. So of course, connection with the bath is essential. I mean, it's there in most cases to even get a magnetization. Okay, nuclear or electron or whatever. To get a net magnetization, you must have some connection with the bath. Okay, so once a bath, this case is of some relevance. In the early days of, say, NMR, you have to look for a sample where you will get a net nuclear magnetization. Otherwise, where's the question of then looking at a resonance and all that? If the populations are equal, then there's nothing to be done. Okay, you don't see a net nuclear magnetization. So it was somewhat fortunate people who first looked for NMR, who found it, is that they looked for samples where there was sufficient interaction between the nuclear spin system and the bath. So that you started out with some net nuclear magnetization, and then you could, with the RF field, you could do various things. Okay. So when the bath is present, of course, populations are equal. Okay. But when no bath is present, when bath is present, so then we sort of wrote down that there is a population difference now, and that we wrote down as this small n, and we wrote that as some n0 e to the minus 2wt. Okay, so there's a reservoir, and you get some evolution, and so there are sort of two processes, if you remember. One is there are transitions within the levels, so that's one relaxation associated, and then there is with the bath. So we had some nomenclature there. There's a 1 over T1, T1 or 1 over T1 that is given, that parameterizes the relaxation due to connection with the bath. And then this W was actually within the nuclear spin system. That was the rate. We looked at when both are present, what will happen and all that. Okay, so in general that we wrote down dn by dt is some difference of n naught minus n by t1 when there is a bath, and then the relaxation rate with respect to the bath is like this. So this we wrote down earlier, long ago, first or second lecture. So somewhat motivated by this and analogy with respect to this sort of situation, Bloch proposed that this now you're looking at nuclear magnetization Z component. He said dm dt, dmz dt equal to m naught minus mz by t1 sort of looks reasonable. Okay, when there is a reservoir, and also this. So here we are referring to this as a nuclear magnetization, but could very well be magnetization rising from the electrons also. So in electron spin resonance experiment, you have the electron Zeeman levels, and then with RF you will excite those and all that. So there, what is the path? Okay, there obviously the electrons are not the path, it's really the lattice which is the path. Anyway, so this is generic. Any whether electron spin resonance, nuclear magnetic resonance, anything of that sort, anything with the nuclear net magnetization, and then it's supposed to relax. Then we said that follows this kind of variation. And this M naught is just because you have a DC applied field, we write it as some chi naught H naught. Okay, so if you're talking about a nuclear spin system, this is the nuclear magnetization, this is the nuclear susceptibility, spin susceptibility, and this is the applied DC field. If you're talking about the electron system, then this is the electron moments magnetization, this is the electron susceptibility, and of course this is the applied field. Okay. So this chi naught is the static susceptibility. So all this is, of course, when H naught, our usual DC field in the Z direction, H naught present, and no RF. Okay.
So what about MZ? MZ is
The Z component of nuclear magnetization.
M naught only. Z component of M naught, or is it?
Right. Z component of M naught. Yes. So whatever is polarized along the field. So this is, of course, if there is no RF, then you have this only this relaxation. In practice, you're going to put an RF and then later switch it off. You have different ways you can do it. So in general, if you have in the presence of a driving field H1, so we have this RF field, then you will of course have additional term. So again, he wrote it down just based on the ideas that we have explained, classical quantum behavior of moments with time and all that. So one is this term, and then you have gamma M cross H Z component. Okay, this H now includes, of course, the RF field. Okay, you have just the Z component, then there is no torque. If you have RF present, then it's going to deviate from the Z direction, and then overall it's described by something like this. So this is for the Z component, and then likewise for the X and Y components, again, by whatever we have learned so far, how the magnetic moments evolve with time, and average XY component should be 0. And if you have no RF field, then the magnetism lines up along the field, so there's no XY component. So in equilibrium, there will be no XY component. So based on this kind of idea, you can also write down dmx dt, X component of the nuclear magnetization, as you have a gamma M cross H X component, and because you want this to decay, right, minus mx by t2. Phenomenological. So he brings in two relaxation times. One which allows to reduce mx and my to 0 with time, and the other which takes care of making the mz to, deviation from mz from m naught to 0 with time. Ultimately, it points along the z direction. It's m naught. Okay. So and then similarly, dmy dt is again gamma m cross h y component, and for the x and y there is the same t2. So this 1 over t2, because you're talking about decay of the transverse magnetization, right? The mz is the longitudinal So whatever is along the field, that is the longitudinal, along the H0 field, longitudinal magnetization, mx, my are the transverse component. So this 1 over T2 is called the transverse decay rate. And of course the 1 over T1 is the longitudinal decay rate. And these equations, so the z component, so then the x and y, whatever order we want to write, these go by the name of Bloch equations. Of course, they are phenomenological. They are based on solid ideas. We have already looked at quantum classical description of spins in a magnetic field. What happens when you apply an RF? What kind of torque, etc., etc. We already looked at all that. How relaxation might happen and so on. You need this exponential variation, right? So we have seen all that. So based on all these ideas, he writes down separate equations, so separate decay rate for the transverse component and another one for the longitudinal component. Okay, here it's a decay, here it's a recovery to the full value. So I don't know in books what are they calling it. It's the 1 over T1 is not exactly a decay rate. It's a recovery. It's a rate of recovery of the longitudinal component of an. Start with. So if you are picturing the presence of an RF pulse, and let's say a pi over 2 pulse, then you start at t equal to 0. You have no longitudinal magnetization, and then it recovers to its full value with time as you remove the RF. Okay, so longitudinal component, it's not exactly decay, it's a recovery depending on your initial condition. So some longitudinal component. Yeah,
So it could also be a decay rate because we have minus of mz over T1.
M0 minus mz.
Right.
So it's a decay of the deviation.
Right.
Yeah. You could call it. It's a decay of the deviation from the maximum. Yeah. Or it's a recovery towards the maximum. Whatever. Yeah. Here it is mx itself which is decaying. Here it is m0 minus mz which is decaying. Sure.
Sir, my question was, so here we're considering one for the longitudinal,
Yes.
and other for the
Yes.
transverse.
Yes.
What if, like say in a material, we
Yeah.
have some planar anisotropy?
Yeah.
Then in that case, these T2s, can they be different for mx and my?
So you're saying if mx and y, you are anisotropy of the nuclear magnetization.
Like, is it even generally
No,
there?
not so electron susceptibility, etc. Because related to the crystal, etc. There you can have anisotropy. Nuclei are really paramagnetic, so there you don't get anisotropy. X, Y, Z. It's all. I mean, whatever choice of axis is the same. It's all isotropic
Only with
paramagnetic.
respect to the field, either along the field or
Along the field or perpendicular field. Yeah. And so he already pictured that you will have different rates, and actually in many real systems, it does happen that here you have in mind from the physical process that you start out with something pointing along the z direction, and with the RF you have a torque, so you deviate from the equilibrium, and then you watch what happens. Okay, so in this picture he has the idea that these mx and my will decay faster, and so he sort of splits it into two processes. One is the process where the spin's transverse component decays, and then after that, this equation takes over in some sense, and then it recovers the z component. Okay.
2 degrees of freedom, I think we can think.
Yes. So it does happen in real, as people are studying. So the 1 over T2 goes by the name of a spin relaxation rate, and 1 over T1, as you know, is called the spin lattice relaxation. As I said, this lattice is generic lattice. It's the bath with which it is exchanging energy. Okay. So in many of us, it's a metallic or magnetic. This bath is really the electron magnetic moment system. Now, this first one arises sort of because if you have a magnetic field in homogeneity, then, as we explained before, at each side the actual field might be slightly different. Also, even the dipolar fields, in some places it will add, if you have dipolar field here, it will subtract, somewhere else it will add to the local field, and so on. So you will get this distribution, and so you get this dephasing. Our classical picture is what? You tip the magnetization, then they are going around like this in the XY plane. Okay. Ideally, if exactly the same field at all sides, then all of them are doing this. This spin is doing this, next one in phase, very coherently. But in reality, that doesn't happen because you have slightly different fields at different sites. So they lose this phase coherence. And so that's the cause for the decay. So if you, here mx is this much, elsewhere the mx may be like this. And so overall you lose mx and my. Okay. So that's what is described by this spin-spin relaxation. Okay. And what is the typical value? So you have, if you take gamma, h local, in what time scale does this decay to 0? Well, it depends on what the typical distribution of field is, local, and then the relevant nuclear gamma. So this should be of the order of 1. Then, this is frequency. So if this is order of 1, then you lose your phase coherence within that time period. Okay. So if you actually just think of the H local as arising from dipolar fields, like not Bohr magneton, nuclear moment divided by R cube, right? That's how the dipolar field varies. Typical R if you take. Anyway, so this comes out to, so tau is of the order of 1 over gamma H local, and so this is like R cube by gamma square H bar. Okay. H local you can take as magnetic moment by R cube. Okay, Gaussian units again, no mu naught, nothing. And then magnetic moment is again gamma H bar. So therefore the gamma square. And so if you take typical gamma, gamma, as you know, gyromagnetic ratio varies from nucleus to nucleus. Proton is the highest at some 42 megahertz per Tesla, and then you have all the way to 1 or less. Okay, so some range of values. Typical several angstrom value for the R, and if you just calculate this, comes out about 100 microseconds. Okay. So in practice also you have seen, you measure T2 and all, in many of these materials you get of the order of hundreds of microseconds, or somewhat more also in cases where nowadays the magnetic field homogeneity is of course excellent. So over a sample from external conditions, there is no problem. You have really at a very fine level, you have very homogeneous field. So magnetic field inhomogeneity does not contribute to this. So in reality, people often write this 1 over T2, the decay of the FID. If you remember, we said there will be RF pulse, then there will be free induction decay. So decay of the FID is governed by this 1 over T2 star, which is combination of the real T2, some intrinsic processes, and then one part due to some distribution of the magnetic field because of experimental issues. Okay, so the FID, which is, you have RF pulse, and then this is the shape of the FID. This decays with some 1 over T2 star, which has a combination of these. So you always have some T2 because of some intrinsic processes which allow for exchange of energy between the nucleus spins. Okay, that is not being present. Nevertheless, the T2s are typically of the order of hundreds of microseconds or milliseconds, something in that range. Okay. Okay, then next, although we know already, so solution of Bloch equations. So at a broad level, we already know what's physically going to happen, but let's at least write in terms of the nuclear magnetization and in terms of the nuclear susceptibility, which is what you are really probing with this NMR experiment, right? So you can, with the DC field and with the RF field along x-axis, right? So we have H naught along K, and then you have H1 field along x-axis. So this is of course the RF field part, and this is DC. Okay. Once you have both these, then you can write the torques. Okay, and so you'll have dmz dt is minus gamma my h1 plus m naught minus mz by t1, and dmx dt is gamma plus gamma my small h naught, where what we are defining small h naught is the deviation from the resonance condition basically. So you have h naught present, and you are transforming to a rotating frame and all that, if you remember. So you have a RF present, and if RF frequency is such that this cancels out, omega z is minus omega, rotating in an opposite sense, we have done all that, then you get precise resonance. But in general, you may be away from resonance, so this deviation is called the small h naught. Okay, so if you are perfectly at resonance, then the small h naught is 0, right? So it's then your magnetic moment is going to precess only about the h1, only about the x-axis of the rotating frame, right? We know all that. So this will be 0, and you'll just be left with minus mx by t. So this is there only when you are slightly off resonance. Okay. Only then this will also exert a torque, otherwise that doesn't exert a torque. Likewise, dmy dt is gamma. Now this has both mz h1, right? You have to now take y component of this m cross h torque. Okay, so y component is xz minus zx type of term. So zx. So for Vaibhav, this is z. This is my z. Minus mx h naught. Small h naught is the deviation from the resonance condition. Minus my by t. So let's say this is my equation C. Okay. So this one is just gamma m cross h. So we are looking for the y component. So zx minus xz. That's all. And the other decay term is there. Phenomenological, proposed by Bloch. So you have a term for the y, and then the way I have numbered, so this is my equation A, which is for the z component, right? So decay of the z component. Equation B is decay of the x component, and C is decay of the y component. So next thing is, we are just looking for small deviations from, our H1 field is small compared to the capital H naught field. That's the first thing. In practice also, we'll also see what H1 is typically you get. But in practice also, the applied field H naught is of the order of, usually Tesla. So 10 power, right? So H naught, capital H naught is like 10 power. So again, all Gaussian units. In Gaussian, B and H are the same. So Gauss, Ørsted, you don't care, you just say anything, it's okay. 10 to the power 4 Gauss or Oersted, whatever you want to say. And H1 is of the order of 10 to 100, not never 100, but something of that order. Okay, so this is really small compared to the H0 speed. Okay, and in this C equation, we'll replace mz by m0 because it multiplies a H1. So any small deviation will just bring a term second order in H1 actually. Okay, so because here it says a product, we just write this mz as m0. Okay, and then as before, let's define this m plus. Remember, this m is the nuclear magnetization, so x component, y component, and z component. So m plus, as before, we define mx plus I my, and you just from these B and C equations, so you will do equation B plus I C, right? So mx plus I my, so you'll get on the left hand side dm plus dt, okay, and similarly the right hand side you'll get some bunch of things. So we just write that. So dm plus dt is minus m plus alpha. I write shortly what this alpha is, plus I gamma m naught h1, where this we have already assumed something here. Alpha is 1 over T2 plus gamma h naught I. Okay, and then we write the solution to this, but we can just see how that appears. So when you do so you will do a mx plus I my. So on the left hand side, of course, you will get dm plus dt. Okay, and on the right hand side, you have to put together terms. I will replace this mz by m naught. So I'll get a gamma m naught h1. Okay, so that was that gamma m naught h1, and the I appears because, of course, I have done b plus ic. So actually, I'm doing this. Right. Okay, so that was that first term, and then the other terms are just combination of. You'll have a gamma my h naught, and then you'll from here you'll have a I gamma mx h naught, so with a minus sign. Okay, and there's a mx by t2, my by t2. So you'll rewrite everything in terms of m plus. So right, so this part is clear. That was just the first term, and the remaining combines into this one. Okay. So the solution to this is, of course, exponential, and so we can write a e to the minus alpha t plus I gamma m naught capital H1 divided by 1 over T2, this quantity here, 1 over T2 plus I gamma H0. then what I'll do is, so we'll replace the m naught by chi naught
H naught.
h naught. This is one, and just to recast in a different form, multiply by, so yeah, 1 by t2 minus, so I want to just get rid of this. Remember, this I is square root of minus 1. Also, at long times the first term is gone. Okay, so we're going to look at what happens at long times. So once this is gone, I multiply by 1 over t2 minus I gamma h naught by 1 over t2 minus I gamma h naught. Remember, this small h naught is the deviation from your ideal resonance condition. Okay, then we say that, so also, just to write in this, so this, you'll get chi naught h naught, okay, and so this gives a gamma h naught. So my omega naught is gamma h naught. So I'm just going to replace, I'm going to skip some algebra just to tell you. So I'm going to combine this, and that is gamma h naught. Then capital H naught plus omega z by gamma is small h naught, this we have defined, and we'll take omega z equal to minus omega, so we are going to a rotating frame basically, and resonance will be when this omega is equal to omega naught. Okay, this is our usual condition. So, at long times this you have removed, and just you are looking at what this reduces to. You want to rewrite this as some a plus ib type of complex number, right? So you work the algebra here, and I write the result. So the transient is neglected. You have put omega z is minus omega, so you have gone to the correct rotating frame, and then later if you put that omega equals omega naught, then that's the resonance condition. So, but before that, what you get from this is that m plus equals chi naught. Remember, this chi is the nuclear susceptibility, not the electrons. You're not still looking at electrons, right? It's just still nuclei. Okay, there's no T1 here yet. So chi naught omega naught T2, then omega naught minus omega times T2, by 1 plus omega minus omega naught whole square T2 square times H1. This is one part, and then plus this complex I, and chi naught omega naught T2, this is the numerator, and the same thing in the denominator, 1 plus omega minus omega naught whole square T2 square, again multiplied by H1. Right, you can sort of very quickly see that this is not so complicated to get. For the denominator, you will see that you have a plus ib, a minus ib, okay, and then plus I, so a square plus b square. So 1 over t2 square will be there, and then this gamma square, h naught square will be there. But then again, the h naught square you can again write as capital H naught minus omega by gamma whole square. No, so the denominator easy to see. You'll get like 1 over t2 square was there. You get that up, and then you'll get omega minus omega naught whole square t square. And likewise in the numerator also, the real part and imaginary part not so difficult to see. Okay. So h1 will be there common, of course, and then for the real part you'll get second term, right? This is because you have an I here, so this multiply of second term with this, that gives the real part. So you have a gamma chi naught h naught, and then when you do a t2 square, so you'll get that in the numerator. So fairly straightforward algebra. So you'll get a t2 square, so t2 and t2. Okay, and then omega, because you have you just need to work the algebra to get this. You'll have a chi naught, omega naught, t2, and so on. So we get mx plus I as what we written here.
So this is basically steady state solution.
Yes, yes. So the transient is gone, and this is the steady state solution. So you have from here mx is chi naught omega naught t2 times omega naught minus omega times t2 by 1 plus omega minus omega naught whole square t2 square multiplying h1, and likewise my is chi naught omega naught t2 and divided by omega minus omega naught square t2 square h1.
So transient term was a to the power minus alpha t.
Yes.
Why we neglected it?
Not neglected. We are not looking at transient response. No, at long times that first term is gone.
Okay. So one question, like a very basic question. So when the transient decays, can that alpha be also thought of as the sort of the decay constant of this transient?
Yeah. What does the alpha contain?
I mean, it is complex though.
Yeah. So it's like you have an oscillatory part,
Right.
and then but a decay part. At resonance, of course, you'll not have the oscillatory part. So
Damped oscillation.
because if you're away from resonance, then you understand, right? Then you'll get precession about some different direction which involves both H0 and H1. So right, so that makes sense. Yeah, this is the decay constant, and if you're away from resonance, you'll also see some oscillation. If you're at resonance, this one is gone, it's just a decay.
And hence the FID.
Yes.
We had this as an exponential.
Yes.
The pulse.
Yes. Yes. So this is what you have for mx and my. So of course, if you go to the rotating frame, then the magnetization is constant, right? X component, Y component remains the same, right? So lab frame. So in the lab frame, it rotates, and we can write. So if you have lab frame is capital X, capital Y, then M capital X is mx cos omega t plus my sine omega t, and m capital Y is likewise the other one combination. Okay. So remember, we have said that H in the H1, so this is the H1 field. So in the lab frame, this looks like Hx naught cos omega t. And remember, we have defined things as that 2H1 is Hx naught. Remember, we said that the HR and HL, there is a field which is going this way and going that way, and a combination of the ones, you get basically a linear field which is increasing, decreasing in a cosine manner. So that's the connection. Ultimately, I mean, you want a field like this. This can be generated as a combination of the right polarized and left polarized. That was done, that this is equal to that just for some algebraic simplicity, because you can work out the equation considering only one of those fields, and so you have both sine and cosine, so it's convenient in many ways. So that was the origin of that. So, but this is the H1 field that we finally have, and so you can write mx. So mx my anyway just pi by 2 off in phase, so it's the same thing. So mx of t is, if you write this as chi prime cos omega t plus chi double prime sin omega t times Hx naught, where I will now identify what is this chi prime and chi double prime. Okay, so what have I done? So far nothing much. In the lab frame, my magnetization is going to vary in this manner. Okay, so at t equal to 0, it's all pointing along the x-axis. As time develops, it now points eventually combination of x and y, then y, and so on. That's what this is describing. I just want to know, so what is this mx and my? I just obtained that earlier. Okay, mx and my are these with something proportional to h1, something proportional to h1 again. So I just need to put these in mx and my, okay, and then identify again that h1 is hx naught by 2, right? And I can then write it like this, where I hx naught. I can write it like this, where I identify chi prime on that prefactor that was there, omega naught minus omega t2 square and all that. So this now looks like chi naught by 2 omega naught t2, I mean, just evident, and then omega naught minus omega t2 by whatever denominator we had, 1 plus omega minus omega naught whole square t2 square. And chi double prime is again chi naught by 2 omega naught t2, and then it will be 1 by whatever is this same denominator. Right, so the 2 comes just because of our definition. H1 is actually, we are thinking of arising from, final field is like this, and then hx naught cos omega t, but the way we have defined this h1, so there's a factor of 2 there. Yeah. So h1 has half of hx naught, And so that's why this half. It's just simple algebra, nothing profound. Okay, why are we doing like this? We eventually just want to write what is the nuclear spin susceptibility in terms of these chi prime, chi double prime. So the response that you get from the system, what it looks like, what is the shape of this function? What is the shape of this function? Okay, this is what we want to drive at. So once again, if we write, this is our H1 field. So Hx C for complex. So in general, if we write Hx with a superscript C, which is function of time, and this is now Hx naught e to the I omega. Okay, then we can identify real part, imaginary part, etc. Our sine, cos, and all that. Okay, so Hx0 is just the real part of the complex function. Okay, and then also we define chi as chi prime minus I chi double. We just define chi like this. Okay, where this chi prime, chi double prime are what we identified earlier. Remember what we did was as a equation of Bloch equations, so solution to Bloch equations in steady state, we obtained mx and my as a function of h1. Then we wrote that in the lab frame and identified something as chi prime, chi double prime, because it's something magnetization proportional to the applied field, h1 field. So whatever is before that is like a susceptibility. So therefore we identified those as some chi prime, chi double prime, and then going further we want to write something as real part and imaginary part of some function. Okay, and so then what is mx of t? I mean what we have obtained earlier. This is just real part of chi hx naught e to the I omega t. So this chi is what I have written here. So if I define my chi as chi prime minus chi double prime minus, then define this hx with a c here, the complex field, if you like, as hx naught. So this is really chi hx c. Okay. Then my x component of, so this is capital X, so lab frame, x component of nuclear moment is real part of chi times the complex h. Okay. Chi also involves already chi prime minus chi double prime. Okay. You can of course verify this. Easy to do. You just have to write. Just check that does it work out. Is what I have said, is that correct? So all you have to do is you have to rewrite this as chi prime minus I chi double prime. Multiply that with hx naught e to the I omega t. Okay. Then also write this as cos omega t plus I sin omega t. Keep the real part, complex part separately, and then you will easily be able to show. Okay. So left as an exercise. So and we'll see what the shape of this chi prime, chi double prime is. Can you draw what is, function is there in front of you? What does it look like? So you can plot as a function of chi prime as a function of omega naught minus omega t2. X-axis is omega naught minus omega t2. Okay, so chi prime is like x by 1 plus x square, and chi double prime is like the omega naught is fixed, all those things don't change. So this one is like 1 by 1 plus x square. Okay, so can you draw what does chi prime look like as a function of x, and chi double prime look like as a function of x? Right, 1 over 1 plus x square is easy to see. Yeah, and the other one is x is there, so there's an odd function, and shape is evident. So one is like this. This is the 1 over 1 plus x square, and the other is something like this. At negative x, of course, you'll see a negative, and then at positive x, you'll see. So this is your this is the absorptive part, right? This is, am I writing correctly? This is chi double prime, and this is chi prime. So your chi prime is x by 1 plus x square. So that's odd function of x. Right, so this one is, so you're looking at as a function of, what was it, omega naught minus omega t2. So this is the absorption signal, and when you're at resonance, you're at omega equal to omega naught. Okay, so you're seeing the total susceptibility of the nuclear spin system. Next question is, the sort of technical part. So in an actual physical situation, what do we have? You have a coil like this. So you have a H0 field applied like so. And then the RF field needs to be perpendicular. So you have a coil with the axis perpendicular. And so therefore this will give you your H1 field. And what is the effect of, so of course, without any sample, this has some inductance. Okay, you have some number of turns, there's a resistance. So there's some impedance, R plus j omega L, whatever, at some frequency. This has some inductance, and so there's associated impedance. Because of the susceptibility of the sample itself, nuclear part, that is going to change. Inductance is going to change. Okay. So, and that is what actually eventually results in a response, electronic response of the system. So, if you have a L0 as the inductance, then again Gaussian units, in the presence of a material inside with the susceptibility, the inductance changes to 1 plus 4 pi. And all this 4 pi business is just because of Gaussian units. Okay. Otherwise, you'll have some mu naught and all that. No, 4 pi will not be there. So I think wherever there is mu naught by 4 pi, replaced by 1, roughly. Okay. So 4 pi is replaced by mu naught. Probably that becomes just mu naught kind of. I don't care. Just to get an idea. So if you have a coil of inductance L naught and you fill it with a material of susceptibility, this is now nuclear susceptibility we're talking about. You want to get the response of the nuclear system. In Gaussian units, it becomes this, and so if you have a frequency dependence, then of course you have a L naught 1 plus 4 pi some pi omega. So this complex susceptibility will produce a flux change, and that's what you will eventually detect. So this chi omega is chi prime omega minus I chi double prime omega. Okay, again this is some technical thing. This is true if your full sample is filling the your coil. So in reality what happens is that you have a sample inside some sample holder often, and you have some limited amount of sample. So you're not filling the coil 100%. So actually there is something called a filling factor, which basically reduces the effect. And if it's only half filled, it's not exactly linear like that, but there's a filling factor involved, and so this one would actually write as times some Q, okay, where this Q is a filling factor. So in reality, you have a coil, there's a resistance also, so you have to take that into account, and you have some sample holder plus sample inside, and it may not fill the full extent of the coil, the full volume of the coil. And so there's a decrease compared to the full value, which will be 4 pi chi, and that decrease has to be accounted in some simple parameters or some filling factor Q. Okay. So then, see, we just want to get an idea of what kind of H1 field is there in practice. Okay. For a minute, if you ignore filling factor, it only reduced the value of the H1. But if you want to just keep this, what is the typical H1 that you get? You're going to get power absorbed, and then how can we write that in terms of what the change of the susceptibility and all that? So this is I'll work out some and then leave some algebra for you. So the impedance, remember, if you have a resistance and a inductance, then in usual electronics you write it like this, J omega L, because somehow the J, you don't want to use the I. We'll not do that, we'll continue to use I. Okay, well, I is square root of minus 1. In electrical engineering, this I is also used for a current. So then there'll be a confusion. Any area of physics, you will always have same symbol, and it stands for different quantities depending on the context. So either you have to know it, or you have to figure out, okay, it cannot be this, it must be something like this. So that's the reason they use J omega L. J is square root of minus 1, but then J can be also current density. So anyway, there can be enough confusion if you're not sure what it is. Okay, so we'll just use I. Okay, current and all. Okay, it's not current; it's complex I. Okay. So you can write this down because there is some resistance of the coil, and then we have said what the inductance is because you have something filling it. So 1 plus 4 pi chi. Okay, and then the whole thing you can write. It looks like R naught plus L naught omega 4 pi chi double prime. So that's a resistive part, and then then you have another part is I L naught omega and 1 plus 4 pi chi prime. Sorry? Reactance is the word that's used for it. Okay. So the chi double prime changes the resistance and that changes the inductance of the coil. And so you can see that you have a delta R by R naught. No, this is the change. I mean, this part is the change, and divided by R naught. That fractional change is just omega L naught by R naught. You know, just this omega L naught, and then you have 4 pi chi double prime. Okay, I've just done, this is my change, so I've just written the same thing. Okay, then this quantity omega L naught, so some basic electronics you have done, this is called the Q of the circuit.
Quality factor.
Now Q factor.
Yeah.
So this is 4 pi chi naught Q. And again, some connection with our experiment itself. When you're actually doing a measurement, so you know, how can you, by doing a measurement, how do you know what is the Q of the circuit, the value for the Q?
Lower resistivity gives higher Q.
So true, but usually if you're at some frequency F,
Delta F.
this is what is the Q of the circuit.
Bandwidth.
So in our experiment, the way we are looking at it, you have a coil and you're looking at, you're tuning it to some frequency. Okay. In the simplest case, 1 over root LC is the natural frequency of this, the resonance frequency, and then you'll not have ideal situation, so you'll get, you know, in the picture that we have on our screen there, you are looking at reflected signal from the coil as a function of frequency. So when you have no reflected signal, then and also you're at the correct frequency, then you're perfectly tuned. And then the spread of this is that because of a finite Q value, Q of the circuit. So more the spread, then lower the Q. Okay, and you can, so we'll calculate based on this what's the Q, but we know in practice it's, you know, between 10 and 100 or so. Okay, so if you remember, if you're at several megahertz, this, I mean, one can take full width half maximum or something, but typically in this range, in practice. Okay. So there is a, I'll not do this detailed, just technical, that's all. So it's there in Slichter. So one can see that. I'll just write so you are looking at energy absorbed. Okay, it's like half Li square, where L is the inductance. Okay, and in terms of the applied field, the energy density is like h square by 8 pi. H is the field, h1 square by 8 pi. So you know, connecting these, one can get what is the h1. So Slichter, he gets it as h1 is like square root of 1 over the frequency you are working on, and Q of the circuit, Q, so power absorbed, okay, divided by the volume. Okay, so then he writes, so this is in some given units, in mixed units, so this is all in Gaussian units, but often you'll use mixed units, so you'll use power in watt, okay, not in some earth derived unit, okay, so frequency is still in megahertz. So in these mixed units, this expression for H1 becomes something like 10 PQ by gamma where it's in mixed units. So H1 is in Gauss, the power is in watt, frequency, since that's how we work, so we want it in megahertz, and the volume, again mixed units, right? So cubic centimeter, is the volume of the coil. Okay, and so you can calculate what the typical H1 value is. Okay, so usually maximum power that we are able to give, you have a kilowatt power amplifier, but remember, if you have too much power, you will get dielectric breakdown even in air, and so you can't use that much power. So maximum P is like a kilowatt, but maybe usually hundreds of watt. So right now also remember, we are only working at maybe 1/3 the power. Okay, so no, never mind, just for a purpose of calculation, you can P power that you provide, and so the power that is absorbed, or 10 power 2 to 10 power 3 watt, right? This in watt. Frequency, I mean, for this calculation, it has some 100 megahertz. Okay, you do measurements typically 10 to a few hundred megahertz, roughly 100 megahertz. Then Q of the circuit, about 100, usually less than that though. Remember, smaller Q, smaller H1, but goes as square root. Okay. Then the other parameter, volume, maybe we don't have that much, but let's say 1 cubic centimeter. Okay, usually smaller than this. So again, smaller volume,
larger. So that's why.
okay, so if you have a small sample, you are killed because of the filling factor. If you have a small sample but a large coil, you get killed because of the filling factor. You have a poor filling factor, so that reduces H1. On top of that, this appears in the denominator here. So you have a small volume, that again kills H1. Okay, so if you want to increase H1, frequency you can't do anything with. You're supposed to work at in a given field, so that you're stuck with that. This power, you have some leeway. If it's not arcing, there's no breakdown, then you want to push as much power as possible because that maximizes H1. Q also you want as much as possible. So again, trade-off. You want large Q, so that maximum power transfer. But we have an issue if you have not a narrow resonance line but a broad resonance line, then the technique, the Fourier transform that is used, it doesn't work well to reproduce the full spectrum. I'll explain at some point what the reason is. So trade-off in everything, but ideally you want as much power in your amplifier as possible. Sharp resonance, so something like this. So you want to maximize this F by delta F. So very small width of your reflected plot of reflected signal versus frequency. Minimize the volume of the coil. Okay, minimize frequency, but okay, there's nothing you can do. So roughly, if you take these numbers, then with these, you can sort of see H1 comes out about 100. 10, then 10 power 3 is 10 power 4, another 10 power 2 is 10 power 6, 10 power 6 by 1, and here is 10 power 2. So 10 power 4 square root. So 10 power 2. So about 100 Gauss, but in reality often much less. Okay. Q is never this much. You don't put a kilowatt, you put several hundred watt. Volume is okay, but you have a filling factor issue. Okay, so all that will reduce, and so you get usually. Then from a practical viewpoint also you can calculate what the H1 is. Practical viewpoint is that how much is, this is the actual measurement. You applied RF pulses of different duration and check which one gives rise to maximum FID. That's your pi over 2 pulse. So this you found experimentally. Right? Again, higher the power, more the H1, smaller the T. Because what is fixed is theta. Theta is pi by 2, and this is gamma H1 T. Okay. You said I want to find out the time taken to tip it by pi by 2. So the angle that you do is fixed, angular variation is fixed. H1 depends on many things. So, and T is actual measurement. So, what is our typical value that we get in all our experiments? Well, you can get small, 2-3 microsecond, typically 5 to 10 microsecond. Okay, so you can't increase power too much. You don't want it too low also. So whatever. So you get roughly 5-10 microseconds. You put that in here. Depends on gamma. So which nucleus you are looking at. Then H1 is then, you know, pi by 2 by gamma T pi by 2. So if you put gamma some megahertz per Tesla, you put T as some microsecond, and you calculate H1, you will find it comes 10-20 Gauss or so. So roughly, I mean, one could increase it by increasing the power. Limitations in everything, there's a trade-off in everything. But just to get a feel for numbers, you know, this is what the H1 depends on. Okay. In reality, you don't want to put too much power because of some practical limitation. Sometimes you don't want a very high Q also, because if you have a broad line, you want to be able to irradiate the full spectrum. So you want not so high a Q. You should be trying to always maximize the volume. Filling factor, and small coil to absolute value of the volume to be small. Okay, because that increases the H1. So instead of a coil like this, we would prefer coil like this, simply because H1 is more. You know, with the same current, you are concentrating more. No, the field density is more. That's sort of the reason. So. Yeah.
So here mu is the RF frequency, right?
F for new RF frequency. Yes.
So also while maximizing the volume, as you mentioned, for the filling factor.
No, so sorry, not maximizing the volume, maximizing the sample filling.
Right, the sample filling. So like, also won't there be any sort of, I don't know, fringe effects like we have maybe in a solenoid?
Yeah, they are. So
like,
good point. So what is the shape of the H1 field? You know, it's going to be like this. So ideally, if you make a magnet with a solenoid, they'll always add some shimming. It's called shimming. You'll add some more turns at the ends to sort of make this way. Okay. We are not worrying about it. Just with hand around the pencil, you wind the coil, and yeah, there'll be, so the pulse shape will not be uniform. Yeah.
So like again, there's a sort of a trade-off.
There's a trade-off there. Yeah. So ideally, you would like a long coil with the sample only at the center, so that it's in a uniform H1 region. If it's too much at the end, then you are picking up this part which is not uniform. Hey, somewhere there is some trade-off. So some of it finally doesn't matter so much, so you live with it. So some of the effects that you, while measuring, could be because of some non-uniform H1. Yeah. So, but important point. So when you make this superconducting magnets, or even other solenoid magnets, electromagnets, so you have magnet like this. You want, you know, as I said, you don't want a field distribution. Your sample should be in very uniform field. So in fact, our magnet there, it has a 0.1 ppm spread over 1 cubic centimeter volume. Okay, so it's very uniform. How do they do that? If you have a simple solenoid, it's not going to work. You always have this fall. So different kinds of shimming coil are added, and there's a whole process. So NMR spectrum is used. The narrowest spectrum that you get is with the most uniform field. So in a typical machine, when they come to install, he'll put a shimming. So you have a shimming coil, and you can put different currents through the shimming coil. So you know, the one will give a field.
So are they like two separate coils? The shimming?
Yeah. Shimming coils are additional separate coils. Yes. And so in different directions also you want to do it. It might produce at the end some anisotropy also. So the winding has to be very uniform. I mean, This is all industry now, so it's done. And then you need to add these shimming coils to make the field even. And then you need to put some combination of currents in these shimming coils to eliminate the effect of these ends. It's never an infinite solenoid. That's the problem. Infinite solenoid is uniform field, but you always have finite solenoid. So the way to do it is you put shimming coils and put different currents to shimming coils. How do you measure? You measure NMR spectrum. The narrowest that you get is with the best shimming condition. That will tell you what this. So in our thing, for different reasons, we didn't do it, but see, our lines themselves are reasonably broad. Even if we have slightly worse than this, we don't care. But for chemistry, when they're really looking at high resolution, they really need that high resolution. So they really need that very high uniformity, okay, minimum spread. Okay, so I think I stop here. So next time we look at spin echo through quantum mechanical approach. So you give a pulse, so how are the operators evolving? One is when there is no H1 in between. So first is you have a pulse, there is H1. So when there is H1, there is a precession happening around the H1 field. Then you switch off the pulse, it's just evolving. So you have a e to the minus I ht by h bar, that kind of evolution. Then again a pulse, okay? So then after the end of the pulse, again evolving. So what does that lead to? If you have them applied in different directions and so on. So that's what we'll see next. Okay, so we'll stop.
Sir, Bloch equation का solution